because I was not, I was having some kind of stomach upset, so I slept early and woke up early.
You were being monitored by so many eyes yesterday. I was
okay.
whether you had a good sleep or not.
Because I was in fact feeling a bit tired because of my stomach upset, and I went to bed early yesterday.
Since yesterday, we have been receiving very good comments and feedback about yesterday's program.
Thank you, sir.
So this is one more feather on your cap, it seems, Krishna.
Sir, I'm nothing, sir.
So shall we start now, Krishna?
Yes, we can go ahead, sir.
Very good morning to 1.5% here online. Once again, I feel honored and privileged in welcoming our guest speaker, Dr. A.S. Krishnan, Associate Professor, Prime Minister of Technology, Coimbatore, for this August online gathering. So I feel privileged and honored in thanking our KPRT management, our principal madam, our CSR, for this wonderful opportunity given to the mathematics department to conduct a two-day webinar on application of mathematics in mechanical engineering. So, being a secondary session, we don't need formal introduction of our Professor A.S. Krishnan. So, I don't want to take much of your time. So, I hand over the session to Dr. A.S. Krishnan. Dr. Krishnan, you can proceed now.
So, shall we begin now?
Yes, sir. Go ahead, sir. All the best.
Yeah. I hope my voice is audible and clear. Okay. In yesterday's class, we had discussed about some concepts on integration and partial differentiation and their applications with respect to work done and Maxwell relation. Both of them are from thermodynamics. Okay. In today's class, we'll deal about applications of mathematical for heat transfer. So what we'll do is we'll first look at differential equations, then also learn about how they're classified. Okay. We'll look at a few examples, then go ahead with ordinary differential equations, then also see how ordinary differential equations are classified, then look at some of the solution methods for ordinary differential equations, but also look at a solution method in particular for a second order linear homogeneous ordinary differential equation. Then coming to the core of the lecture, the application, heat conduction, we will see how the governing equations is developed for fin heat transfer. We will also look at two different methodologies. One is analytical, another one is numerical. The objectives of today's learning is to develop the governing equation for fin heat conduction subject to a given physical condition, and to obtain temperature distribution for the given condition by analytical and numerical techniques. So once we have achieved our objectives, we should be able to obtain temperature distribution for a fin with 1D heat conduction and convective loss for different boundary conditions, and also estimate the heat transfer rates and fin performance for a fin with 1D heat conduction and convective loss, again for different boundary conditions. Now let us look at what do these differential equations mean. These involve ordinary or partial derivatives of one or more dependent variables on one or more independent variables. This is a very general definition. Okay. Now in the slides you can see some examples of differential equations. Now the first one is d square y by dt square equal to g. This is an equation that governs the physics of a freely falling body. And the next one is m d square y by dt square equal to mg minus k dy by dt. Suppose a mass of m is freely falling, and also is subjected to air resistance, then this is the equation that governs the system. And coming to today's application, d square theta by dx square minus m into theta equal to 0. So these all belong to a class of equations called ordinary differential equations. What we can see is y is the independent variable for the first two equations, and theta, y is a dependent variable for the first two equations, and theta is a dependent variable for the last equation. In all this equation, we have the dependent variable being dependent on only one independent variable. And these are called as ordinary differential equations. On the right hand side, we have the first equation is the very popular Laplace equation, dou square w by dou x square plus dou square w by dou y square plus dou square w by dou z square equal to 0. This is also, in short form, it is also written as del square w equal to 0. The next equation is the heat equation, again a popular one, a square into the Laplacian of w equal to dou w by dou t. We are using the short form called Laplacian. Okay. And the third one is a square into Laplacian of w equal to the second derivative of w with respect to time. And this is called the wave equation. And these come under the category of partial differential equation. In all these three equations, we can see that w is the dependent variable. It depends on x, y, z for the first equation, and it depends on x, y, z, and t for the second and third equation. Okay. Now, coming to ordinary differential equation, the scope of the lecture is limited to ODE. The general form of an nth order ODE can be written as a naught of x into dny by dxn. In fact, n is nth derivative of y with respect to x. Likewise, plus a1 of x plus d of n minus 1 the derivative of y with respect to x, and so on, up to an minus 1 of x into the first derivative of y with respect to x plus an of x into y equal to f of x. This is a general form of an nth order linear ODE. Later on, we'll see what is non-linear ODE. Now we can see that a0 of x, a1 of x, etc. and all, they are functions of x. They're also called as coefficients. And on the right hand side, we can see f of x. F of x is called a non-homogeneous term. It is also called as forcing function. Aka means also known as. Okay, fine. Now, the reason why we call it as forcing term is it represents the external influences that drives a system, or the effect of external influences. That's why it is called as a forcing term. Okay. Now, instead of having functions of x, if the coefficients are constants, then it is called as a nth order linear ODE with constant coefficients. What we have done essentially here is replace all the functions a0 of x, a1 of x, and so on up to an minus 1 x. In fact, yes, we have an of x also. We have replaced that with a0, a1, etc. to an. Okay. Now, what do we mean by nonlinear ODE? If ODE is nonlinear, it has appearance of y in the form of a power or a radical. For example, d square y by dx square minus dy by dx plus y square. Sometimes it also has derivatives and products. Okay. Right. Okay. So, looking at some of the methods for solving differential equation. These methods can be broadly classified as analytical method and numerical method. In analytical, we have several methods: variable separable, and use of integrating factors, and use of the characteristic equation, and series solutions method, Laplace transform. In fact, I would like to stress upon the fact that these are only some of the methods of solving the differential equation analytically. And in numerical, we have finite difference method, finite volume method, finite element, and control volume based finite element method, level set method, and the same applies here also. And this is the list is not limited to 1, 2, 3, 4, 5 for both analytical as well as numerical. And it is to be noted that many of the methods which have been listed above can be used for solving partial differential equations also. Because many times we have uh, partial differential equations being converted into ordinary differential equations, okay? And this helps us in solving them relatively easily. Okay? And differential equation, both partial differential equation and ordinary differential equation, they come in variety of sizes and shapes. Okay? What I mean, so there is no general method. There's a particular method by which we can solve all of them. It is something analogous. So for example, human beings come in different shapes and sizes. There's nothing like we have a common dress for them. Each one, for each one, the dress has to be tailor-made. Okay. And again, drawing an analogy between dresses for human beings and solution methods to differential equations. Okay. For some people, or some people may not be interested, and for example, some people may not be interested in wearing a trouser. Okay. So what can be done is you can wear a dhoti. This is something like a numerical method. Now we'll have a small illustration of a differential equation and a solution for differential equation. Okay. Let us consider the second order differential equation y double dash minus y dash plus 6y equal to 0. Y double dash means d square y by dx square. Okay. And y dash means dy by dx plus 6y equal to 0. Y is a function of x alone. So it's an ordinary differential equation. The highest order is second, so it's a second order derivative. Okay. So second order ODE. Okay. And it is homogeneous. You don't have any forcing terms on the right hand side. Okay. Now it is known that y1 equal to e power 2x and y2 equal to e power 3x are the solutions. Okay. Now that so, we can examine whether y1 equal to 4 e power 2x and y2 equal to 3 e power 3x are also solution. What you have essentially done here is put some constants for both y1 and y2. Okay. Y1 is 4e and 4 e power 2x and y2 equal to 3 e power 3x. Okay. And we can also examine with another pair of constants, 7 and 2. When we plug in all these things, we will be able to notice that all of these are solutions for this ordinary differential equation. So that saying, we can generalize as y equal to c1 e power 2x plus c2 e power 3x will be a solution for this ordinary differential equation for every choice of C1 and C2. Okay. What we mean to say is, if there are two solutions, y1 equal to e power 2x and y2 equal to e power 3x, a linear combination of these two solutions will also be a solution. So C1 is a constant, C2 is a constant, and this is a linear combination. So now, how to find out C1 and C2? The constants in C2. About the boundary conditions, we'll discuss a little later. Okay. Now coming to the solution methodology for a linear second order ordinary differential equation. Well, let us consider a homogeneous linear second order ODE with constant coefficients. Okay, and again the forcing term is 0. D square y by dx square plus p dy by dx plus y equal to 0. And we are replacing d square y by dx square by y double dash just to have some kind of a convenience in writing in short form. So y double dash by plus py dash plus gy equal to 0. Okay. So whenever we've been solving, straight away what we do is write the auxiliary equation. Okay. So we also will try to learn how did we get this auxiliary equation from this equation, the original differential equation. Okay. Let us consider the function e power mx. This has got some specialty. When we take the derivative of this function with respect to x, okay, for example, if we take the first derivative, we get m e power mx. When we take the second derivative, we have m squared e power mx. So its derivatives are all constant multiples of the function itself. So y equal to e power mx can be considered as a possible solution. You can always substitute here and check it out. Now, assuming that y is equal to e power mx is a solution, then it must satisfy this differential equation. So y equal to e power mx is being substituted here. So first term is m square. E power mx we have already taken out as a common factor. Then we have p into m y dash is m e power mx. Okay. Now this has to be 0. E power mx obviously cannot be 0. So m square plus pm plus q should be equal to 0. So this is called as the auxiliary equation. Okay. Now this is a quadratic equation and the roots can be readily obtained. m1 comma m2 is equal to minus p plus or minus square root of p square minus 4q by 2. Okay. I'll give you a minute's time for just assimilating this. Okay, looking at the roots, we see two possibilities. Three possibilities. Let us look at them. Roots are real and distinct. Roots are real and equal. Roots are complex and distinct. Okay, let's just go back to the slide. Okay. If p square minus 4q, this quantity is going to be 0, then you have m1 comma m2 will be equal to minus p by 2. And if p square minus 4q is positive, then we have minus p plus or minus is positive, the square root of a positive term. That is again real. So we have minus p plus p square minus 4q by 2 and minus p minus square root of p square minus 4q by 2. So we have two real and distinct roots. And in case if the terms within the square root is negative, then we have then this gives rise to complex roots. Again, they are distinct. This is what has been stated in the slide. Roots are real and distinct. We have p square minus 4q greater than 0. In this case, we have y1 equal to e power m1x and y2 equal to e power m2 into x. m1 is not equal to m2. Okay. Now let us see this one. Ratio e power m1x by e power m2x equal to e power m1 minus m2 into x. And this is not a constant because x is a variable. Now, why should we bother about doing this one? Because we need to ascertain that the solutions are linearly independent. That said, they are linearly independent because this term is not a constant. Then we can have a combination, linear combination of e power m1x and e power m2x to be a solution, or general solution for this case. So we have y equal to c1 e power m1x plus c2 e power n2x. Okay. Now what happens when roots are real and equal? So in this case arises where p square equal to 4q. So what is the root? m1 comma m2 equal to minus p by 2. And this gives rise to one solution, y1 equal to e power m1x. Okay. Now we have only one solution. How to find out the other solution? And again, we have a relation v equal to integral of 1 over y1 square e power minus integral p dx, and that gives x. Okay. So y2 equal to x e power m1x. So this is the other solution. So what are the how did we arrive at this v equal to 1 over y1 square e power minus p dx. Okay. Now, there is a technique that in getting the solution, that if one solution is obtained, the other solution can be obtained. So here what we do is, the other solution, we are assuming that instead of the other solution being a constant multiple like what we have here, other solution is c into e power m1x. Instead of that constant, what we do is we have a function of x itself. And we are assuming that y2 equal to a function of x into e power m1x. Okay. And that function of x, that is called as b. How do we find that function of x? What we necessarily do is we substitute this in the original differential equation. The steps has not been shown here, and you can have a try on those steps. It will be interesting. So once we substitute here, we have two solutions. One is the regular one e power m1x, and from this only we get the other solution y2 equal to x e power m1x. Okay. Now these two, are they linearly independent? Yes, they are linearly independent. When we take the ratio, like we took the ratio here, e power m1x by e power m2x, we got e power m1 minus m2 into x. This is not a constant because x is a variable. Likewise, y1 by y2, we get 1 by x. And x is again not a constant. So we can have a linear combination of these two. That's what has been written over here. So c1 e power m1x plus c2 e power m2 into x. So if the roots are real and distinct, this is the general solution: y equal to c1 e power m1x plus c2 e power m2x. And if the roots are not distinct, they're real but not distinct, y equal to c1 e power m1x plus c2 e power c2x into e power m2 into x. Okay, we discussed, in fact, we listed out that there are three possibilities. Okay, two possibilities have already been discussed. The third possibility is that the roots are complex and they are distinct. Whenever p square minus 4q, the term is not zero, we get distinct root. Depending upon whether it's going to be greater than 0 or less than 0, we get real or complex roots. Considering the case where b square minus 4q is less than 0, we get two complex roots, m1 and m2. And we are aware that complex numbers can be written as a plus ib, a real part plus I times an imaginary part. And since we have plus or minus square root of p square minus 4q, we have a plus or minus ib here. Okay. Now the two solutions are e power m1x. What is m1? A plus ib. Okay. A plus ib into x. That is equal to, we can take out e power ax commonly outside. Take this one. We have e power ibx. And e power ibx can be written as cos bx plus I sin bx. This is by Euler's formula. Okay. In a similar way, we can write for e power m2x also. So m2 is equal to a minus ib. So we have e power ax into e power minus ibx. So this gives us e power ax cos bx minus I sin bx. Fine. Now, what we do is we add the equations 1 and 2 and divide by 2. When we add equations 1 and 2, the imaginary terms, they get cancelled. We get 2 e power ax cos bx, and divide by 2 we get e power ax cos bx. And the next step what we're going to do is 1 minus 2 by 2i. When we do that, the real term gets cancelled off. So it's going to be e power ax sin bx. And now we got two solutions. Are they linearly independent? Yes, of course. So we can take the ratio and then check whether they are linearly independent. Are they? So e power ax will get cancelled. We get cos bx by sin bx or sin bx by cos bx, depending upon how the ratio is being taken. So either cot bx or tan bx. That's going to be a variable. So these, we can have a linear combination of these two as a general solution. E power ax factor has been taken out. So we have y equal to e power ax c1 cos bx plus c2 sin bx. This is how it comes when the roots are complex and distinct. In fact, one might note that we don't even need to write the second equation. Once these equations known, once the first equation is known, we can directly write. Okay, we can directly write the solution as the real parts, combination of real parts of this this the right hand side of this term. What are the real parts? E power ax and cos bx. Okay. Once we multiply this by I, then it becomes complex. Okay, or imaginary part. So the real part of this one, these are e power x cos bx, and then we have e power x sin bx. Okay. So this is going to be the general solution for this case. Okay, now coming to fin heat conduction. So what you could see is most probably you would have guessed this is a fin of a fish, might be a shark, a great white shark. We all know about the film, no? The Jaws. It came in 4 parts. Jaws 1, 2, 3, 4, and this fin is very popular with us. And this is a dinosaur. This has got fins all over its body. So the reason behind putting these pictures are fins are not only found in artificial systems like what we'll be seeing in the next few slides, for example, in transformer cooling, electronic chip cooling, and then for compressors to dissipate heat from engines. They're also found in case of natural systems. Okay. In fact, the basic purpose of for having a fin is to have what is called as an extended surface area. Okay. And this extended surface area not only increases the possibility of heat transfer, but also mass transfer. Okay. Now let us proceed further. As I told earlier, this extended surface are also known as fins, or you can call it either. Fins are also called as extended surface. In this picture, it shows cooling of a 4-cylinder air-cooled Franklin automobile engine. It belongs to this engine belongs to 1910, more than 1 century before. And these are the fins. These longitudinal stripes are the fins. Let's not worry about the other components present over here. Now, these fins are also used for cooling of electronic equipments. This picture shows Pentium processor. Okay. There's a processor beneath this one. Below the aluminum sink, this is actually aluminum fins, a set of aluminum fins. Below this, we'll be having the processor. The processor will be mounted below the fins, or the fins are mounted above the processor. In this picture, it is more clear. The P4 with the cooling shroud raised. This is called the cooling shroud. Okay. Here you can see the fins more clearly. Like differential equation, fins also come in wide shapes and sizes. These are called as spin fins. Such fins are these fins are generally found in electronic equipment cooling, and such fins can be found in the radiator of an automobile. And these are fins over an engine. Typically, it's an engine for an aircraft which were used earlier, called radial engines. These are called as compact heat exchangers. They also have fins. And we have a twin cylinder engine here, Harley Davidson. And many such applications are available for fin. Now we'll move on to the equations part of it. We'll consider a general fin heat transfer analysis. Here we are going to consider only a single fin. It is always easier to single out something and analyze. Okay. So what we do is we single out fin and start analyzing. And this fin has a variable cross-sectional area. It is something like a truncated cone. Okay. What we do is we take an elemental strip out of it, okay, and then apply the energy balance. Okay. What happens? And it is assumed that this fin is attached to a surface that has got a temperature higher than that of ambient. Now what happens is, since the temperature of this base is higher than that of ambient, there's heat transfer flowing from this base through this fin to the ambient. Of course, through the lateral surfaces also. So when we do the energy balance for it, what we get? So let us take, for example, we are taking a strip of thickness dx, which is at a distance of x from the base. Qx equal to, this Qx is equal to Q at x plus dx. The heat transfer at this surface equal to heat transfer at the right hand side surface, okay, plus heat loss by convection through the lateral surface. We have the left hand side surface, the right hand side surface, and the lateral surface. Okay. Now here the heat transfer at the left hand side surface and the right hand side surface, it acts through the cross section area by conduction, and from the lateral surface area it happens by convection. Okay. Now what happens on the left hand side phase? Qx equal to minus KAC dt by dx. This is by Fourier's law of heat conduction. Here K is the thermal conductivity of the solid and AC is a cross-sectional area at distance x. Okay, fine. Now Q at x plus dx can be written as Q at x plus dqx by dx into this strip distance dx. In fact, one may recall what we discussed on this the partial differential equation yesterday and all. So we wrote some similar terms like this. Okay. Now when we expand this one, what happens? Qx equal to minus KAC, we can directly substitute what we got from here, minus KAC dt by dx minus K into d by dx of AC into dt by dx. Since it is explicitly, we can see that the cross-sectional area of the fin, it varies along the length. So we cannot take this out of the derivative. Okay, so it has to come within the derivative. But interestingly, we have not stated anything regarding K. Had we assumed K also to be a variable, in fact, it is the other way around. We have assumed K to be a constant. So if K is not a constant, then this also should go inside this one. Okay. So this is the equation what we get, expression what we get for Q at x plus dx. And by Newton's law of cooling, the lateral heat transfer can be calculated as H into dAs. dAs is the surface area of the ring, okay, multiplied by T minus T infinity. T is the temperature of this element. T infinity is the temperature of the ambient. And one more thing that needs to be kept in mind is that we are assuming that T is a function of only x, and it does not vary. It does not vary within the cross-sectional area. For example, if we take any distance x, we get a circle, and within that circle, T does not vary. That is the assumption what we're making here. Okay, let us proceed further. When we substitute for Qx and Qx plus dx and Q convection, what we get is this equation. d by dx AC dt by dx minus h by k das by dx t minus t infinity. Okay. So we are in fact expanding d by dx of AC into dt by dx. So we get d square t by dx square into DAC by dx, what we have written here, into dt by dx. In fact, we have divided throughout by the cross-sectional area, okay. And this is the final equation what we get. Okay, so in arriving at this equation, we've made some assumptions. One is that the thermal conductivity K, it's a constant, and when we also assume that H is a constant. That is the heat transfer coefficient, it does not vary. Okay. There are possibilities that the heat transfer coefficient can vary. But even in still air, the heat transfer coefficient can vary from the base until the tip. Okay. But for engineering purposes, an approximation can very well be made that the heat transfer coefficient is a constant. Now we'll see what happens when the cross-sectional area is also a constant. When the cross-sectional area is a constant, let us look at what are the terms that will get shipped out. The DAC, the second term has got DAC by dx. Since the cross-sectional area is constant, DAC by dx is 0. So the second term goes off. Okay. And what we're left out is HP by KSC T minus T infinity. Okay. Now, this is for a case where the cross-sectional area is a constant. Okay. And we can see two pictures. There are two profiles of the fin. On the left-hand side, we see what is called as a rectangular fin. The cross-section is rectangular, and here it is a circular fin. These, the one what we see on the right-hand side, they are also called. These things are also called as pin fins. Okay, and the dimensions of geometric details of both the rectangular fin and pin fin are given here, and this general fin heat transfer analysis and uniform cross-sectional area analysis, they have been directly adopted from reference number 3. We'll see what is reference number 3 little later. Okay. Now, coming to this equation, we see d square t by dx square minus hp by ksc into t minus infinity equal to 0. We are always fond of writing things in a shorter way. What we do is, we have theta of x. We define t minus infinity as theta. Okay. Since t is a function of x, theta also will be a function of x, and this is called as the excess temperature. Okay. We also define one more parameter called m, where m square is hp by KAC, or m is equal to square root of hp by KAC. When we substitute these two in this equation, what we get is d square theta by dx square is equal to, minus m square into theta equal to 0. Fine. And looking at this equation, we should recollect something else. What kind of equation is it? It's a differential equation. It's an ordinary or partial differential equation. We have only one independent variable, that is x. So it's an ordinary differential equation. What is the order of the equation? It is, the highest order is 2. So it's a second order differential equation. And m square, we have assumed that h is constant. The heat transfer coefficient is a constant, k is a constant, and for a given fin, in fact, the cross-sectional area is also a constant, and for a given fin, the perimeter is a constant. So entire term m square, it becomes a constant. It's a constant coefficient. Second order ODE. Is it a linear or non-linear ODE? It is a linear ODE. And are there any forcing terms? No. The right hand side does not contain any forcing terms. So it is a homogeneous second order linear ODE with constant coefficient. Right. Now we'll go back to the discussion on ODEs. Now y double dash plus p into y dash plus qy equal to 0. Fine. In fact, for the equation what we are discussing, we have only y double dash, some parameter analogous to y double dash, that is d square theta by dx square. There is no first derivative of theta. So we have only the first term, the third term, relatively simpler. So for this equation, what was the general solution that we arrived at? General solution is e power mx, c1 e power mx plus c2 e power into x. Okay, we just need to check out what happens whether this p square minus 4q is equal to 0 or not. Okay, let us check that. When we draw an analogy, what we will be able to see is we are likely to have a solution like this. Theta of x equal to C1 e power mx plus C2 e power minus mx. Right? Okay. So depending upon what we have, the boundary condition, the solution will vary. Now let us look at the various boundary condition. Okay. Looking at the applications of fin, they are primarily used for increasing the heat transfer rate. Okay. For example, when we consider cooling of a processor, what we do is we attach fin on top of it, either directly or indirectly. Okay. The reason why we are attaching is the processor must not cross a limiting temperature beyond which it is likely to fail. Most of the electronic equipments, they fail beyond 80 or 90 degrees Celsius. Okay. There are equipments which can work more than that also. So that said, in fact, electronic equipment cooling is one of the evergreen areas of studies. As long as electronic equipment still exists, we need to cool them. Okay. So for cooling, mechanical engineers are necessary. Okay. So both electronic engineers as well as mechanical engineers are required. Okay. So coming back to our problem, okay. Having said that, some limiting temperature, most of the times the limiting temperature, TB, the base temperature is prescribed. Okay, fine. So when the base, so that is at x is equal to 0, at x is equal to 0, T is equal to TB. Okay, or by the definition of theta or the excess temperature, theta is equal to T minus T infinity or TB minus T infinity. Theta, so in fact, theta B is a constant. Fine. Now we need to give one more boundary condition, that is at the tip or at x is equal to L. We can have three different possibilities for them. Just like that, we gave a fixed temperature or a specific temperature at theta is equal to 0. We can always have fixed temperature at theta is equal to L, or at x is equal to L also. Right. Now, if the fin is very long, okay, then at the tip we can experience the ambient temperature itself, or the tip temperature will be equal to ambient temperature. Okay, we can have an analogy for it. Okay, in our household, suppose if you want to have, if you are boiling milk or heating some foods, what we do is we keep it on the stove, and we don't, when you switch it on, we switch on the stove and take the vessel from the stove, we use a pair of tongs. Okay. The pair of tongs, they are actually not very short, they are very long. Okay, we use a pair of tongs, take it and okay. Okay, and at the end of the tongs we don't experience any heat. Okay. That's because the tong is very long. Okay. And likewise, if the fin is very long, the tip temperature can be specified to be the same as that of ambient. In such a case, what we have is theta at L equal to Tx, that is TL, that is also T infinity. So theta will be 0. This is one case. The other case is we can have looking at the general solution, we can guess that the temperature profile of the fin will exponentially decay. Okay, since it exponentially decays, what will happen is the heat transfer rate near the base will be very high, and as we go along the length of the fin, it will be very less. Okay, so here the temperature will be profile is almost flat. Okay, when it is flat, what happens is this term dt by dx becomes negligible. When this is negligible, we can approximate it to be 0, or we can say at the tip, the heat transfer rate is necessarily, or it can be approximated to be 0. The third and a little more complicated case is that we have some convective heat loss from heat transfer, some heat transfer rate from the tip of the fin also. And this is generally, anything which is not zero is always a little bit difficult to handle. So instead of giving a convective boundary condition at the tip, what we can always do is we can have a little longer fin. We can have a little lengthier fin. Okay. And then say that the convective, we have adiabatic tip or the heat loss is zero at the tip. So what purpose is the extension of the fin serve? When we look at the tip area is not zero. It has got some finite area, right? Okay. Now what we're going to do is, so suppose if we are going to insulate this tip, or if we're going to approximate that there is zero heat transfer rate, where actually heat transfer happens, then we are making some mistake. So in order to compensate for that mistake, what we do is, instead of having area here at the tip, we are having an extended length of the fin that is equivalent to the same area. This is sometimes called as corrected length. Okay. This also gives a reasonably good result. Although we are approximating, this gives better results. Okay. Now we'll move on further. Okay, fine. Now we have the temperature distribution and the heat losses. Okay. Now we have, again we said, three different cases. In four cases, we have one is a convective heat transfer. Okay, that is H theta equal to, we have convective loss H into theta. What is theta? Theta is T minus C infinity. T minus C infinity at L equal to minus K d theta by dx. Okay, fine. This is one particular case. This is the boundary condition what we need to adopt. The second case is d theta by dx at L is equal to 0. This also we discussed. And coming to the third and fourth case, they are almost similar. One is theta L is equal to theta at L is equal to theta L, a prescribed temperature. The next case, it is theta at L equal to 0. Okay, this is for an infinitely long fin. So for this case, when you substitute these boundary conditions in this general solution, you'll be able to get the exact solution for the temperature distribution. And these are the temperature distribution. They are given us a ratio of two temperature x's. Theta b is known. Theta b, in fact, it will be the maximum. So when okay, it will be at exact when we plot theta versus length, the maximum value of theta will be 1 because at x is equal to 0, theta is equal to theta b. So we have four different cases corresponding to this one. Okay. Now coming to fin heat transfer rate. Okay. Now how do we calculate the heat transfer rate? I have not explicitly given in the slides. Okay. No, we go ahead with this one. Okay. By Fourier's law of heat conduction, Q equal to minus KAC dt by dx. Okay. Now let us look at this fin. Whatever energy comes, it comes from the base, this area. Okay. And what is the x value at this area? Base is at x is equal to 0. Okay. So if we calculate minus KAC into dt by dx, the temperature gradient at x is equal to 0, then we will be able to get the value of heat transfer from the fin. Okay, this is in fact one of the methods of getting. In fact, it is also the easier method of getting the heat transfer rate. Okay. So as expected, depending upon the boundary condition, we have different heat transfer rates. Okay. Suppose if we have a convective tip, we have one heat transfer rate. if you have an adiabatic tip, you have different heat transfer rate. Likewise, for temperature prescribed, the theta L is not equal to 0 and theta equal to 0. Right? So depending upon the boundary condition, we have the temperature distribution and the fin heat transfer rates also. Fine. Now, fins are for particular applications. Okay, they are expected to solve some purpose. That said, we always want to measure or estimate the performance of fins. Performance of fins are defined by two parameters. One is called the fin effectiveness. It is it is denoted by symbol epsilon f. F denotes fin. Okay, and fin effectiveness is defined as the ratio of heat transfer with fin to without fin. And how do we find the ratio of heat transfer rate with fin? We have these expressions. Using these expressions, we can find the ratio of heat transfer with fin. So how do we find out ratio of heat transfer without fin? Let's get back to the okay. Now, to find out the ratio of heat transfer rate without the fin, what we do is we just take out the fin, and the fin, when it is being taken off, it leaves an area. For example, here it leaves this area open. And what is the temperature of this area? It is T base. Okay. So to calculate the heat transfer rate without fin, what we do is we take H into the temperature of the base minus temperature of the ambient multiplied by this area will give the heat transfer rate without the fin. Right. There is also one more term called fin efficiency. It is defined as ratio of heat transfer rate, that is actual heat transfer rate with fin, okay, to what? To the maximum possible heat transfer rate with fin. We have whenever we attach a fin, the heat transfer rate increases. Okay, but what could be the possible maximum heat transfer rate? Let us again go back to the fin. I think the viewers must excuse me for going back and forth. I'm sorry for that. Okay. Let us take this one. Okay, we know that the temperature of the fin, it decreases from base until the tip. Okay, from here it decreases. Okay, so near the base, the fin has a very high heat transfer rate, and as we go away, the heat transfer rate of the fin decreases. Okay, suppose if the entire fin is at the same temperature as that of the base, then the heat transfer rate from the fin will be the maximum. Okay, that is how we calculate the maximum possible heat transfer rate. So these are typical curves for fin for fin 1D fin, the temperature profile along the with the distance. So this is for stainless steel. Stainless steel conductivity is very low. Okay, the next profile, the second profile is for aluminum. Okay, and the third profile, the topmost profile is for copper. Okay, let's go further. So far, whatever we have done is we have discussed the analytical method of solving the governing equation of fin to obtain the solution. There's also one more method called the numerical method. We'll quickly rush through this thing because we don't have much of time. Okay. These are the various steps. Geometry and physical phenomena as the input, and we divide the geometry into very small parts, apply the governing equation to each part, solve the set of equation. Unlike only one equation, we get several equations, simultaneous equation. Okay, and then we get output of the field variables. Field variable here is a temperature. So in the next slide, we'll see in more detail way for the fin. Input is a fin, dimensions of length L and diameter D, base temperatures at Tb. It is exposed to ambience of T infinity temperature and heat transfer coefficient of H. The thermal conductivity of the fin is constant at K. We divide the geometry into very small parts, okay, and apply this equation to all these parts. So we'll be having as many number of equation as the number of parts we have. So what we need to do is to solve all the equation simultaneously or by iteration. Typically, we'll be having a matrix like this. Okay, and the output field variable at each control volume. Okay. Now, when you look at this one, we have a discontinuity in this slope. That is because of the way in which we have divided. Okay. Obviously, we cannot divide the geometry into infinite parts. We have to divide only into infinitesimal parts. So each part has a temperature, and the next part has a different temperature. That means we will have a step variation in temperature or a discontinuous variation in temperature. Okay. But we approximate it to be continuous. Okay. Let us see how this can be done. There are several ways. Basically, what we're going to do is when we look at this equation, this is a differential equation, and we have transformed this differential equation into an algebraic equation. Okay, how do we do this transformation? That is called discretization. There are several methods, and one of the method is using by Taylor series. Taylor series, we have T of x plus delta x equal to T of x plus delta x into dt by dx plus delta x of whole square by 2 factorial into d square t by dx square plus and so on. Likewise, when we take at a point at x minus dx, we have dx minus dx equal to T of x minus delta x to dt by dx plus delta x square by 2 factorial into second derivative of temperature and so on. Okay, and suppose if you want to if you want dt by dx, what we can do is we can take dx to the other side and write T of x plus delta x minus T of x by delta x plus higher order terms. Higher order terms involve delta x and delta x square and so on. Okay. So we can also write dt by dx as T of x minus T of x when we take the second term. Okay. So this is called backward differencing. This is called forward differencing. So you could possibly try 3a plus 3b, 3a plus 3b, and 3a minus 3b, and see what happens. Now, our objective is not to find dt by dx, but d square t by dx square, because we have only the second derivative. And the second derivative temperature. There are no first derivatives of temperature. Let's recall these two equations. We have these two. So when we have 1 plus 2, when we add 1 and 2, we get the second terms in the right hand side get cancelled. Okay, so this is the equation what we'll be getting. D square t by dx square plus equal to T of x plus delta x plus T of x minus delta x minus 2 T of x. These are written in terms of T, temperature, can always non-dimensionalize and write as theta. Okay, so here when we look at this one, we have T of x, we have a term T of x, we have term on x minus delta x, and we have term on x plus delta x. Likewise, we had I minus 1 and I plus 1. So we can express theta I in terms of I minus 1 and I plus 1. So when we vary I from 1 to n, okay, we'll be getting a matrix for this. We'll see how the matrix will look like. Here we have made some small manipulation. Instead of taking theta as t minus infinity, we have taken a t minus infinity by tb minus infinity, which means that theta is normalized, and we are using a term called psi, where it is x by L. When we do this, this equation, the ODE transforms to this kind of ODE, and this is the ordinary differential equation, what we are going to transform into an algebraic equation. So when we do this, we get this one. This is a simplified form, and we have m square into L square into del c square plus 2. This, in fact, is a constant for a given condition of fin and the fin geometry and ambience, base temperature, etc. And once we fix a grid space also, this entire thing is a constant. So when we write this, we actually get a matrix form. When we solve the matrix, we get the same equation. This is a typical matrix what can be formed. Okay. think we'll wind up with this. We are almost out of time. And in case if there are any feedback, any discussions or queries or clarifications, you can ask. And these are the references. In fact, these are very good books on mathematics, differential equations with applications, and by George Simons, and Foundation Mathematics for Physical Sciences by Rayleigh and Hobson. And this one, this is the reference 3 is a source from which I have taken the Finn heat transfer analysis. All of you might have heard of this book by Heat and Mass Transfer by Frank P. Incroper and David P. Dewitt. And it has been expanded by Professor Theodore Bergman and Professor Adrian Levine in the 7th edition. It's a wonderful book for heat transfer. And I thank, once again, I thank the management of Coimbatore Institute of Technology, my principal, and my head of the Department of Mechanical Engineering at CIT. And I have always got tremendous support and encouragement from CIT. Okay. And thank you, KPR Institute, for inviting me, for giving me an opportunity to interact with you. And in particular, I would like to thank Professor and Head Department of Mathematics, Professor K.S. Ramaswamy, for choosing me as the guest lecturer. Thanks a lot. Sir?
Whether your presentation is over or still you want to say something?
Yeah, my presentation is over. Presentation is over, sir.
Anybody has asked any queries or doubts regarding this? So first question, sir, you can see the chat box under some.
Yes, yes, f of x in nth order ODE, y is n times differentiable. What about equity? The equation is so, and even when we differentiate n times, f of x, it gives f of x on the right hand side. What actually happens is, in fact, f of x itself is a derivative. Okay. It is the most of the times what we have is when we develop the governing equations. Many times, whether it's going to be fluid mechanics or for thermodynamics or heat transfer or any other structural mechanics, what we do is we take a differential form. Okay, and this differential form is helpful in the for the reason that it is one of the easy way for converting to algebraic equation. And we all know that algebraic equations are always easier to solve than differential equation. And one more question is there. We have the second question will come to it a little later. Suppose we have more than one fins attached, then what will be the differential equation and the boundary condition? Is there any change? Yes, changes will be there. But for a given fin, or even going to be more than one fin, the geometry is same. So the differential equation is going to be the same. But what we will just go back to the slides and see. Let us take, for example, this fin. It's a rectangular fin. Okay, we have here it is only one fin. What will happen if you're going to attach one more fin here? Here. Okay. Now we need to make some assumptions. When we attach one more fin, physically what happens is the temperature Tb is likely to decrease because there is more heat transfer from the surface. Okay, that is one part of it. Another one, assuming that the fin has the same thermal conductivity. Okay. What about the ambient? T infinity and H. T infinity, probably we can assume it to be constant. Okay. But what about H? H, when there are more than one fin, the air between the two fins may not be able to freely flow. because here we have only one fin. Even if it's going to be by natural convection, we have hot, if the fin is hot, the ambient is cool, we have the air being heated over here and it starts flowing up. And after this air flows up, it is being replaced by cold air just coming in. Okay, but so we will be having, so the circulation will be happening. And because of the circulation, we have some particular value of heat transfer coefficient. Now, when we consider one more fin on top of it, what is going to happen is there could be some localized flow happening between the two fins. Okay, so the heat transfer coefficient is no longer going to be the same. Okay. It could possibly decrease. Okay. So we need to take a smaller value of heat transfer coefficient. And there are several other complexities also involved in it. One of the thing is called the boundary layer. Instead of one may question like, okay, instead of having two flat fins which are placed horizontally, why not place them vertically? And this happens so many times. Even in that case, there's something called boundary layer that develops over a surface. Okay, whenever there is a fluid flow, there is a boundary layer developing on the object or on the solid surface, and the boundary layer developing over one of the fin can interact with the boundary layer developing over the other fin. Okay, so these boundary layer interaction can again reflect on a change in heat transfer coefficient. So we can, the governing equation is not going to be different. Only thing is the values what you're going to take in the governing equation will be different. What is the software you are using for putting graph from ODE? See, suppose if you're going to solve the governing equation, when we get an exact solution, okay, in terms of an exponential form, you can always use Excel, okay, or any other software. And explain it last wave equation, Laplace equation. We need to derive the equations. So I don't think we'll be having sufficient amount of time to explain on this particular question. I think we can interact on this a little later also. Is there any other clarification? Any other questions or feedback or something?
Hello, sir. Could you explain your email ID on the screen so that
sure. Yes.
One of the users, the viewers can easily contact you to clarify your doubts.
Sure, sir.
So askrishnan@cit.edu.in. Is it not, sir? Dr. Krishnan?
Yes, sir. Yes, Krishnan, cit.edu.
Before concluding, I want to put two questions, sir.
Yes, sir.
Shall I ask, sir?
So you can. If you know, I'll answer, sir.
So why the researchers, engineers, mathematicians have not discussed differential equations of order 3 and higher numerically? Only they have dealt only first order and second order. They have not gone for third order or higher order. Is there any reason behind that?
I could give a guess answer for that. Fortunately for us, most of the problems that we come across, they can be described by first order equations and second order equation. Even second order equations itself, they're very difficult to solve in some of the cases. Let us come. So that said, going beyond the third order, beyond the second order, third order and all, I'm not sure whether practical applications. One is that, and even if you have practical applications, when we look at the derivatives as such, this second derivative is likely to be less than the first derivative. We'll just have a look at this one.
Krishnan sir, whether I can, yes, you say, sir, you want to say something, it seems. Go ahead, sir.
Yes, I'll just, we'll just have a look at this one.
Yes, sir.
When we look at the curve, this is obviously a nonlinear one.
Yeah.
So when we take the first derivative, this first derivative is going to vary from here to until the end. But when we take a second derivative, it is likely to be smaller, and hence third or fourth derivative probably may be less than that. So I'm not sure whether it will assume any real significance. And in case if you have anything to add, I'd be happy to hear from you, sir.
Just I have some idea in my mind. Whether it is correct or not,
Yes,
you have to ratify it, sir.
I don't think I'm the right person to ratify it, but I can always enjoy whatever you're telling, sir.
So most of the problems in science and engineering can be modeled only as a second order PDE, whether it is true or not, sir. It is the convention I am having in my mind. Whether your idea and my idea coincides or not, sir. Or you can put it in different forms, sir. As an engineer, you could answer.
In fact, when I was preparing for this lecture,
yeah.
In one of the books it was written as we are modeling systems, but whenever we model, we are doing only an approximation. The real thing, obviously, it is extremely difficult to achieve. But it shouldn't deter us from modeling, because at least we will have some kind of an approximation, so that we can work on that approximation, have some factor of safety, and go for the next step. If you really want to go for the exact solution and all, sometimes you may not be able to achieve it. One very popular example is the exact solutions of the Navier-Stokes equation. In fact, people say that even if we research and find out and what are the condition for which the Navier-Stokes equations will have exact solution, that itself is a great thing. The full Navier-Stokes equation is in fact it is out of bounds of analytical methods. That's where numerical methods help a lot in taking us further and getting us more insight into the problem and all.
In the second order PDE, namely the one-dimensional wave equation,
Yes,
y double t equal to alpha square into y double x. Using the method of separation of variables, we are segregating this second order PDE into two first order ODE, and we are finding this. Is it not, sir?
Yes, variable separable method.
Variable separable method. The second order ODE, sorry, PDE converted to two first order ODEs.
By product solution, we are assuming product solution and then
product solutions.
Yes.
And both are, I think, in my opinion, both are homogeneous equations like this. Is it not, sir? Both are
yes.
Using variable.
Sometimes convert. Yeah. So sorry, sir. Sorry, pardon me, sir. Sorry.
Using the variable separable method, we are converting the second order PDE into two first order ODE, and we are solving by our usual auxiliary equation, complementary function, particular integral, and general solution technique. Is it not, sir?
Yes, sir.
Whether this could be applied to third order also, 3 PDE, whether 3 ODE is possible, or so far I haven't seen in any other book or research journals a lot like that. Third order PDE they haven't tried. Is there any significant reason for that, or it is a convention, or something like that? I need a reply from you, sir.
In case if you have not found, I have also not found, sir. No, the thing is, I mean, honestly speaking, I have also not come across, or I have not done on how to, I have not explored on how to convert a third order PDE into 3 ODs or something. Then probably we need to have if you're going to extrapolate, then we can have product solution, for example, into x of x into x. Let us consider that equation.
So you are a honest man, no doubt, sir.
We can just point out something, and somebody who may be interested in they can take up further. Generally, for if it's only x and y, it depends only on x and y. We take w as a product solution, x of x into y of y. And we say that x is only a function of x and y is only a function of y, and then we separate it. We could try extrapolating this as x of x into y of y into z of z, and divide that equation by x, y, z, the function x, y, z. So where x and when one is a variable, the other 3 or 2 will be treated as a constant. We could try, but I do not know whether extrapolation will work or not. But it is really interesting to try. In fact, I just to add something to it.
Yes, sir.
We were discussing on this Finn equation.
Yeah.
D square t by dx square minus hp by ks into t minus infinity. This in fact happens at steady state. Once an unsteady parameter comes, then the solution becomes very complex.
Yeah.
Okay. So in fact, the unsteady we can deal unsteadiness separately without having any hp by ksc or something. But when some let us say d square t by dx square equal to 1 by alpha square dou square t by dou x square equal to 1 by alpha dou t by dou t. That can be solved relatively easily. Okay, fine. And likewise, d square t by dx square minus hp by ksc into t, this also can be solved. Okay, these two sets of equation are relatively easier. But once the right hand side becomes a derivative, okay, then it becomes exponentially difficult. And numerical methods, in fact, help a lot in circumventing such difficulties. But what I would like to add is, even while we are dealing with numerical methods, we should first understand what is the nature of the differential equation. Most of the times we deal with, as you said, we deal with partial differential equation. We should ascertain the nature of partial differential equation, whether it is going to be parabolic, hyperbolic, or elliptic. So depending upon that, we have to vary the model of the numerical solution also, sir.
In parabolic equation, like one-dimensional heat from unsteady state, we are doing numerical methods.
Yes, sir.
What is the guarantee that the solution is always stable or convex? Is there any criteria? Is there, sir?
Yes. In fact, there is something called stability criteria.
Stability criteria.
Stability criteria is there. Whether the solution is going to converge on each and every. There's something called von Neumann stability analysis. There's a formal way of doing that. So depending on that, we have our intervals. I just go to this slide. So here we have only delta x, but still nothing. We can go ahead with this one. In when we deal with transient, we have not only delta x, but we have delta t. Okay, and as Professor rightly pointed out on this stability or guarantee of solution, okay, we cannot choose the value of delta x and delta t in a very arbitrary way. There's a particular ratio in which we have to take, and that ratio depends on each and every differential equation, what is going to be converted into algebraic equation, but also what is the scheme we are going to use. For example, here we are using forward differencing, and here we are using backward differencing, and in the next slide we are using central differencing. So the stability not only depends upon the value of x and delta t to be chosen, but also on the scheme. And in fact, stability analysis again is a separate field of research.
Sir, the last question, sir. I don't want to take much of your time. Already you are there. In the elliptic equation, the uwx plus uw equal to 0 or parabolic equation. At the grid points, you are using either the standard formula or the cross averaging, diagonal averaging. We are forming equations and we are solving. Is it that, sir?
Yes. The thing is, sir, in numerical method, we know that there is more than one way of doing the discretization, and each way can give rise to a particular solution that can in fact affect the solution and also the stability. So we must be very careful in what is the way we are choosing. For example, in when we look at the elliptic equation, ellipse is like it is like this one. Okay. So it is a bounded curve. Okay. So whatever happens in the boundary is going to affect what is inside the cell. So whenever we take point inside the boundary, suppose let us take, for example, we have divided the ellipse into several parts. Okay, when we take inside the boundary, what we're going to do is we ensure that our numerical scheme is such that the point of conservation, okay, is equally influenced by all the neighbors. So this is a case of, yes.
My doubt is,
Yes, sir.
At the selected mesh points,
Yes,
the
sir.
boundary values are given. Let us suppose that this is a square boundary.
Yes, sir.
At the boundary values are given at the selected mesh points, you are evaluating the values either using cross averaging or diagonal averaging. Isn't it? Standard 5-point formula, diagonal 5-point formula. Okay. And you are forming a set of equations. And you are solving those set of equations by standard methods.
Yes.
My question is, what is the guarantee that the set of equations arrived will always converge?
Again, in fact, the answer is more of an open-ended one. There are several things which play into the convergence thing. Now we'll look at the scheme surface. We'll just a moment, sir.
No problem.
Now we look at see whatever questions you ask pertains to the third and the fourth one. Apply the governing equation to each part and solve the set of equation. Okay.
Yes, sir.
So while doing this one, we transform the differential equation into some particular algebraic equation.
Yeah.
And the way in which we do this, okay, will affect the solution. That is one. This one is the discretization itself will form a criteria. Okay, and the next one is how many parts are we dividing the geometry. If you're going to divide into if it's going to be divided into not many number of parts, like whatever I have shown here, we can have this actually shows a temperature variation. No physical system will have a temperature variation like this because it is a step. It's something like a step variation. The slopes are discontinuous, and this is a result of the kind of a grid what you have chosen. So this also this is another area where this is another factor which affects the solution.
Okay, sir. Thank you very much.
Okay. But just a small thing to add, although there are so many advances in numerical methods, analytical methods still have their own classicality. So in fact, somebody who is interested in analytical method, they can always pursue with it. There are a lot of scope for, personally, I believe a lot of scope for research is there in analytical method also.
Okay, gentlemen. Thank you very much, Dr. Krishna.
Thank you so much, sir.
For your wonderful and informative and nice presentation, sir. You splendid, sir, really.
Thank you, sir.
The day one, Dr. Krishnan covered computation of work done in compression, Maxwell equations. In day two, he covered analytical solution to field heat transfer and numerical solution to field heat transfer. So we have been receiving commendable feedback from all the participants. And it is interesting to see that we have more than 1,000 views. For yesterday 1,000 views, today 1,000 views. Totally we have on an average of 1,000 views for this session. And also we have got viewers from abroad, from Dubai, from Oman, from Kuwait, and also from Telangana, Andhra, Orissa, Rajasthan, and Bihar. So I hope everybody has enjoyed this session. And any clarifications pertaining to these two lectures can be easily clarified with Dr. Krishnan, who has shown his email ID. Once again, on behalf of KPR-EET Management, Principal Madam C. Sir, and on my own behalf as Professor and HOD of KPR-EET Maths Department, I render great thanks to Dr. Krishnan, who has accepted this assignment in spite of his very busy schedule. So I thank Dr. Krishnan on behalf of everybody. Thank you, Dr. Krishnan.
Thank you so much, Professor. Thanks a lot, sir. Thank you for the opportunity, sir.
Okay. Shall we wind up, sir?
Yes, yes, sir. Wish you all safe and pleasant times ahead, sir.
Thank you, sir. Thank you, sir. Thank you, sir.